Good afternoon, everybody. Welcome back from the break. First off, probably on Wednesday of this week or Friday, we're going to do a walkthrough for the midterm stuff. I'm still prepping up sort of the slides and everything else. I'll get you guys that back by the end of the week for sure. We are now roughly 2 weeks away from presentation stuff. This is the current updated timeline. Now, there's two things that just happened. I need to go to Zurich right here. So we have a couple choices. We can slide down, so we basically take these tops here, so everything just gets blocked out. We could slide down and one of these goes over here, in other words, earlier in that point, in which case we stop at this time, or we slide down and these two start earlier. So what I'm saying is we could, any two people or any 2 days could be Wednesday and Friday of like these two blocks over here, which means we can finish off earlier or we run into April. Does anybody have a preference of like, does anybody want to go sooner and get it done sooner? Yeah.
I can't go sooner.
No. It doesn't have to be these individuals. And what I'm saying is anybody on this grid can elect. We need two people that says, I will present in this Friday slot, which means you don't have to go later. We can rebuild it. And everybody's like, no.
Could that be on the 6th instead?
This would be the 6th, yes.
I can. I'm on the 16th. I might be able to go soon.
You could go on the 6th, sure.
I'm 9th, and I can go earlier.
On the 6th as well. Okay, so why don't we take that? So Boris, you go up, and then you are on the 16th, Haley?
Yeah.
Okay, so why don't we move those two? So you two go up, I'll reschedule, shuffle like that too. What that'll end up doing is that we'll only take this one point over here, but that means also these two are off in that part. Yeah?
Right. I'll just send you an email. I am getting back on the 16th, so I can come in earlier than that, but I'll send you an email.
You're getting back on the 16th? That's cool.
The 15th.
The 5th, that's fine.
I just wasn't sure if you were going to move me like a week earlier, but I'll send you an email.
Well, let me take a shot at it. Again, this is not our A plan. We will adapt, right? But again, I just wanted to give you guys the opportunity, instead of us dragging on into the middle of April, we could still knock off everything done if we shuffle things around. So appreciate it, guys. Thanks very much. Okay, other reminder, if you haven't done so already, please email me your selected paper, and it should be done as okay, again, a lot of people have kind of sent, it could be any of these. I've tried to give feedback. If I'm still waiting for one, I do apologize if I haven't gotten back. It's been a nuts couple of weeks. Point is, I would like your final papers so I can aggregate them together. I'm going to put them on the website, or on the Canvas site, so everybody can download them in advance, basically, so you guys can start to look and see about which ones are sort of available. I'll tie them together with the individual presentations so you can download them in the point. Bare minimum, right? Before your talk, you need to have the paper up in advance so the students can actually go take a look at it before your time, but also your slides should be there by the evening for the next day, basically something that people could download and then follow on. I'll also give you guys on Wednesday the rubric we're going to use for scoring against this. So it's a simple questionnaire. What I'm going to ask is the following. So basically the way that the presentation part is going to work out, like I said, is you have sort of this general framework. You're asked to sort of present a paper in this kind of SCQA type format. You're asked to sort of give your opinions and sort of, again, teach it like a course. There's a topic, and you've got half the class to do so. Part of your grade will also be your interaction. So while you guys are here, what I'm going to be doing is asking you to ask a question of whoever on here, right? So part of your grade is not just what happens at the front, it's your interaction with the speaker as well. Also, what we're going to do is something, basically, it's like a peer review. I'm going to assign every one of you some other person that you must review, which means you have to come to that person's day, right? Like, again, it'll be anonymous. You will not know who you are reviewing in that point, so I'll pass it off and I'll give you an individual assignment. If you cannot make that day, that's fine. Let me know, and then we'll just adjust. But that's why I'll give you guys an in advance warning of this is who you've been assigned, which means your job is to be the critical evaluator, sort of reviewer two for whatever that presentation is. What that really constitutes is you're going to be filling out a form of what your opinion is on every part of it. You'll be asked to basically evaluate and rank it, almost like if you've ever done a paper review, if you've received a paper review, it's kind of like that, where you're basically giving constructive feedback of how the person went. Those comments will be passed back to the student, so keep it anonymous in that sort of capacity, right? And again, keep it friendly, nothing like, oh, that person's stupid face and blah, blah, right? Like, no, you never know. Does that make sense? Okay. What we're going to do then, so with that part, we basically got the next sort of 5 classes. We're going to focus on selectivity, catalysis, and control. What this does is cover these last kind of topics. This is really that next generation stuff, talking about the rate behavior and everything else we discussed, but now into these other applications. So these are things like where does selectivity come from? How does that fall back into sort of the rate equations and the energy level diagrams you've been discussing? Specific applications like the Curtin and Hammett principle are embodiments. These are tools that you can use for actually sort of enhancing how you might think of a reaction mechanism, and just think of it as the applied side of a lot of what we've been going through. And then getting into some of the demonstrations and stuff into the correlation spectroscopy and organocatalysis. So, very basic. Everybody's probably seen this and it's been grilled into you at some part. In organic chemistry, we have 3 general levels of selectivity. Now, again, it depends on what you guys have sort of been taught up of how you think about doing synthesis, but the sort of methodology I was most familiar with starts off by this kind of chemoselectivity, regioselectivity, stereoselectivity kind of basis, right? The nature behind it, the energy level surfaces, is really no different, but this kind of hierarchy and ranking is something that you probably have done, but we'll just talk a little bit more implicitly about it. So first off, chemoselectivity. You guys have all heard this. This is the whole point that you see in sort of first, second year organic chemistry, where we rank functional group transformations based on which ones will and will not happen, usually according to a bunch of empirical rules. Like, so for example here, the addition of an organolithium to a ketone rather than an ester, we think, or like, again, if you had to say in your own words, why does this happen? Why are you getting this sort of selectivity?
I believe ketone is more electrophilic than methyl ester.
Right, so we're saying a ketone has the reactivity of the ketone is higher, therefore that pairing is going to be better, right? This whole strategy, right, you've probably seen energy level diagrams or reaction webs that sort of says what will work and what won't. Just within the carbonyl set, you guys are already familiar with this kind of a sequence where aldehydes are on one end and, carboxylic acids and stuff on the other. That energy reactivity sequence, though, is talking about stability. So something like electrophilicity. Think of that, remember, this is kind of coming back to valence bond theory. Reactions happen, something like this. You're talking about the addition of a pair of electrons into the carbonyl. So which side of the equation is that for valence bond? Are we doing HOMO or LUMO for that kind of a transformation? If I'm trying to describe what orbitals are involved in that step right there, how might you break that down? Yeah. Exactly. You are donating electrons from the HOMO, right, where you have electrons. So the nucleophile, it's the highest occupied. That means the LUMO is the accepting side. What we're really trying to describe here, right, anywhere that you've got your arrows leaving from a space means that you're adding into an antibonding orbital. That's what's being accepted. And you're breaking a bond as a result of that. So SN2 is a result of nucleophile donating into the antibonding sigma orbital between your carbon and your leaving group, or things like that. So this is the antibonding pi electrons as well too, right? So these are things that you guys have already done a lot. The nuance here that's just to go back to that level of specificity. The other thing that's really implicit with this kind of selectivity, though, is it's about a matched pair, right? So if you remember about things like Diels-Alder reactions, we can talk about allowed and disallowed reactions, not just based on, okay, the electrophile is more reactive in this sort of case. You're talking about a nucleophile to electrophile, which means those orbitals have to be similar in energy relative to each other. The nucleophile has to be reactive enough, high enough in energy, and the electrophile, lowest occupied, has to be low enough so that there's a similar energy level balance. That's key because remember, any type of 2-compound addition is a pairwise addition. We can say certain things react not just because most reactive and least reactive in that sort of case where there's a sort of a major minor, but what you can see, especially when you start coming back to catalytic systems, some pairing matches will work and others won't. So there's about making this a better nucleophile will make certain reactions work, as well as making this a better electrophile, right? So you have both of those two things to look at. It's not just about one or the other. But the chemoselectivity sequence that we've gone through, this is something that you guys have some implicit knowledge on. Next line is regioselectivity. This is the region or the position of a reaction. So in this case, we're doing an HBr addition. It is always acting to the alkene, so there's nothing special there. We're not choosing which alkene between the two. We're talking about the addition to the same alkene, and it's about the geometry of those two products, where you're not looking at diastereomers. These are regioisomers of different products where what we're doing is sort of like, substitution patterns. So in this one here, you guys all know this. Why does this happen this way? Like this is a law or a rule we talked about. If you had to explain why you see this particular regioselectivity, what's going on?
Tertiary carbocatalysis.
So the part here we're saying is that this is a two-step mechanism. Protonation produces a carbocation, so you have a high energy intermediate. That high energy intermediate, so we start here, we make a high energy intermediate, which is our tertiary carbocation, which is then nucleophilically captured to go to our second step, right? Something like this. So the thing that we're going to practice through is coupling back some of these type of diagrams or these outcomes back to the energy level diagram that explains it, right? Because the other way you could try to do this is if I had to sketch what happens, why do we not get this minor one? Well, we still have to make a carbocation, but we're just implying that up here, this would be our surface for a secondary carbocation, which we're just not accessing, right? So this is a selectivity at the intermediate step rather than onto the product. So again, regioselectivity cases like this are still this example where we're doing a single addition to a single functional group. Common intermediates are usually what we're advocating here. So this is where they're both carbocationic intermediates. It's just you have geometric differences between the two. Now remember, any of these kind of simple explanations on these kind of two different paths has to be weighed against what we talked about before. These energy surface are hypersurfaces with multi-dimensions. You don't just have one path to one molecule. You have a terrain where you have different geometries, bond breaking and forming all kind of happening coinciding with each other as well too. But it's a good first approximation to kind of give you that selectivity. Last level is stereoselectivity, and you have both diastereoselectivity and enantioselectivity. So first example, a reaction that undergoes diastereomeric control. Very common ones are things, again, back to our carbonyl chemistry. This is reductions to different sp2 sort of centers. So you guys have seen these before. These are things like Cram chelation control. These are the geometry or models that we apply that talk about which face of one geometry that we might be running into. In the end, again, what you're doing here at this lower level is you're saying that it is happening at the ketone only. You're saying that's happening where the hydride is adding to a single center, so it's not different regioisomers. Now you're just talking about topology, top or bottom face of a particular addition. In this case too, once again though, if we're making the two different products, we're still coming back to something where like a bulky hydride donor is going to give us one facial selectivity over another, where we're still coming back to an energy level diagram argument. Remember, if you remember, and you guys have done like Cram chelation control and things like that, right? The various models of approach. We're still saying that there's a mnemonic that says the hydride, aluminum hydride, is going to coordinate to the carbonyl first. That's going to produce a complex where the two different potential geometries, where you can set up like a Newman projection and say one face is favored over the other. It's just giving you a geometric control where the stereochemistry in this case is actually part of the molecule itself. In this case, the reason that the two products are diastereomers is just because you start with a single defined stereocenter, and we're adding a new stereocenter to that one where you have different populations as a result of that one. So in the end, the next level down is your enantioselectivity and enantiomer controls. The one thing I do want to sort of quickly comment on is this a language part. You may have heard of certain reactions as being diastereoselective, enantioselective, versus enantiospecific or diastereospecific. Do you guys know what those two things mean? In your own words, how would you describe it? Yeah.
I think enantiospecific is whatever you have as a substrate, it'll give you a specific enantiomer, but enantioselective is your substrate in stereochemistry will dictate your stereochemistry.
Yeah, like when we say specific, and an SN2 reaction is a really good example of this is an enantiospecific reaction. We're saying that if you do a substitution according to an SN2 reaction, the mechanism predisposes a single geometry of your product. So, and we're not saying that, oh, all SN2s give you 100% EE. There may be other things like stereo scrambling or the enantiopurity of your starting material. We're just saying that in a particular geometry, in this case, if I have a carbon-iodine bond, whatever geometry I have here, I must undergo inversion because that's the nature of how this mechanism works. It's impossible to do by any other kind of way. So any reaction that is a specific reaction, you have to get a certain kind of a product. The other one that's very common is the E2 type eliminations. It's the geometry you're looking for there has to be this anti-periplanar elimination that gives you that specific that specific transition to your product. So what we're saying when we say something is enantiospecific or diastereospecific, the mechanism is basically the geometry of your product is determined by the transition state itself. It's actually baked into the orbitals that you're actually getting. When you say something is selective, that's where we're saying that, for example, the reduction of a carbonyl. The reduction of the carbonyl in the previous slide, those are selective reactions, not specific. A hydride could approach from either face. There's energy differences we can exacerbate to give you more of one than another. But as a result of it, you could get either possible product. Last one, too, I want to just bring up, too, in terms of definitions is what we call topicity. Is this also familiar with people? If you say something is enantiotopic or diastereotopic? Yeah, generally? Okay, so just quick review. What you're mentioning when you say something about topicity, it's a way of talking about a molecule that doesn't have that stereochemistry yet. You're talking about the potential relationship of that group once a stereoselective or a diastereoselective reaction actually has happened. So in this case, the starting material is our alkene. We have the black, the red, and the blue group. If we looked at the two, the relationship between both the hydrogens top and bottom can be defined by replacing those with something of a different CIP. So in this case, the way that you could sort of assign it is if I were to replace the red hydrogen with the deuterium versus the blue hydrogen with the deuterium, look at the two possible products and ask what is their relationship to each other. This is the classic sort of Chem 123 experiment of what are these two to each other? Are they enantiomers? Are they diastereomers? Are they just regioisomers in that sort of case? So in this case here, the two possible geometries, they are not stereoisomers. Well, they're stereoisomers, but specifically they're diastereomers of each other. So the relationship we would say is that these two are diastereotopic to each other. Now, why does that matter? Like, what is that designation? How do we use that designation typically? If you've run into this sort of process before, yeah.
Like on an NMR spectrum, diastereotopic protons show up as two separate peaks, but enantiotopic is different.
Yeah, like what you're saying is that even though they're equivalent hydrogens, they have different chemical environments because of what they could be turn into. Yeah, NMR is probably the number one that you're going to run into. Remember, NMR is just the molecule whispering to you about the possible energy states and stability that it actually has. It means that diastereotopic groups like this could be differentiated by some other chiral agent that's going to have diastereomeric transition states, versus if it's enantiotopic, you must go in with a specific strategy in mind that's going to help you to do that differentiation. If NMR already sees them as different, chemically they're already different on their own, so you don't need a chiral molecule to potentially react with those two. Versus enantiospecific or enantiotopic groups, excuse me, this is just the same sort of example, blue versus red, switching those two diastereomers in this molecule that becomes the new, you're going from an achiral molecule to one that now has formally an R or S center. You have created a pair of enantiomers to each other. These would not show up differently in the NMR, and as a result, if I wanted to differentiate those two protons, you have to have some kind of a chiral strategy in place where your transition state needs to be differentiated by usually some other stereoselective event. You're going to have a chiral ligand or something associated with some sort of that part of this. Again, it just helps out to make sure that you kind of do this first pass, especially if you're going through and you're trying to come up with ways that you might split and differentiate a material. If you're moving too quickly and you're kind of coming up with ways that you might do a sort of separation, if you don't do this check, especially with very large molecules with weird symmetry, you may not realize that the groups you're trying to actually split or differentiate may actually in fact be enantiotopic to each other just based on where the internal symmetries of the molecule are. It's just one of those cases that stopping and kind of doing the formal analysis can really help you when you're doing molecular planning. But anyway, at the core of it all selectivity comes down to energy levels. What we're saying is at some point you are going to make one or the other product. In this case, this is actually a cycloaddition where you might be getting two different possible products. And again, you've probably seen the geometry like this. We're looking at the blue versus red two paths. We can differentiate these two. We're going towards the blue side. We typically assign that as the kinetic product, versus going toward the red side, we might be getting our thermodynamic product. And again, all we're really trying to emphasize with that part is looking selectively at part of the curve. So when we say something is a thermodynamic product, we're saying given some case where two products could exist, And the way to read these graphs, if you haven't played this before, is now what we're doing is we're starting right here and we're saying left versus right. We're evaluating two possible pathways. So usually we use this butterfly sort of notation where instead of starting from the left and moving to the right, we're dropping the reaction in the middle and we're asking it to compete. And usually that's why showing it in this kind of book example where we have those two is just a simple way to rank energy levels against each other. The other way to do it is you fold them on top of each other and you're just looking at them overlaid where you have both transition states on the same point. But sometimes, again, it's just for clarity, you'll see it represented this way. Now, in general, thermodynamic product does not necessarily mean that the kinetic product must have a higher energy state, right? There's a possibility that one molecule can be both the thermodynamic and the kinetic product. This is just one of the classic examples that you'll see where there's kind of an A versus B choice. What we refer to here as the thermodynamic product is just the final energy state over here, but there isn't really implicitly some reason why every kinetic product must be higher in energy than the other. What we're talking about, the kinetic product, means we're only looking at the transition state, right, between the actual two. So this is where the manifold that you want to kind of pick up, and when you're talking about selectivity, is always going to be some version of this, depending on how many other transition states that you're looking at. So something I want to encourage you, and something we'll practice through in this next couple of weeks, is really talking through this part of if you have a reaction that is giving you a certain product, the joke in organic chemistry is like, oh, why are you getting this one? Oh, it's probably under thermodynamic control. No, it doesn't seem to be. Well, then it's got to be kinetic, right? It's one or the other is usually how we split it out. But I mean, being intentional about what you think this hypothetical energy surface looks like, even if it's an abridged one, is something that we're going to practice in. So in this case, if the chemoselectivity was going towards a certain product where under kinetic control, we're saying that this one may form faster to make this material here. Now, given this diagram, this overall one here, like this entire species, if that entire energy surface existed, yes, we may be starting in the middle. This is the kind of system where you may form the blue product faster, but over time, it is possible for the blue product to reformat itself over into the red product, right? So you guys have seen that sort of part too, where you can have conditions which will select for the kinetic product, which means I'm trying to run the reaction and limit usually the amount of thermal energy present to only allow the fastest to form material to be generated. But there's possible that the same reaction manifold might initially form the blue product, but then over time, we're going to end up making the red product. Now, what absolutely has to be possible for that to be true? Well, yeah, remember, microscopic reversibility says that on the scale of the universe, turning into diamond is also reversible. It's reasonable energy barriers. But yes, you're right. Like, it needs to be, what we're saying is, this is now what we're talking about, is some general relationship completely coming down to those two heights and their relative barrier. The selectivity based on the kinetic point is not just, okay, yes, this one is lower, but we can calculate by how much based on that gap right there. And that gap is referred to as our, usually, this is delta, delta G, double dagger, right? This is the difference in energy states between the two transition states. Yeah?
How big can that be for it to be able to go from the kinetic product
Over to the thermodynamic? You can calculate that.
Okay.
Right? So this is where one thing I have an Excel sheet that we're going to work through that lets you actually punch these into something like Copasi and run the time course, right? You can actually say that based on this scale right here, that's the maximum theoretical ability to select blue versus red. And we need to know how big that gap is because usually we're going to select between two kinetic products. That gap is whatever it is. And if we're saying that one has to form faster than another, that's a rate difference between going blue versus going red. So based on that, you can say, well, based on the value of that delta delta G, I can go back to something like Arrhenius and say, what temperature do I need to make those two Ks big enough to get me a 10-to-1 ratio? Or am I going to be fighting with 4-to-1, 2-to-1, 1-to-1 as much as I can, right? The size of that gap is really just, that's whatever the universe has handed you of the amount of energy difference you've got to play with. From that gap size, your delta delta G or your EA basically, right? You can go back to Arrhenius and say, at what temperature can I take that delta delta G and expand it wide enough for something that I need to be useful? This is kind of like doing the linear free energy relationship stuff that we did, that by knowing roughly what this is, you can make a call and say, Well, if I run this reaction at minus 100 degrees, I will get my 10 to 1 selectivity I'm looking for. Do I want to do that or not, right? But now you've got to make an objective call. Or go back to the drawing board and find another transition state or another catalyst that allows me to widen that gap by a certain amount. That energy difference, and this is something where, it's the RT and that delta delta G is what defines how big of any selectivity can be. That's just on the kinetic side. Back on the other, how big does it have to be? Well, if I was going to park all my molecules over here, and then over time I want it to slowly hop back and then hop back, I need to know not just my delta delta G, but now I need to know this guy, which is your delta delta G naught, or your energy state difference as well too. So it's the combination of how big your energy barriers are for your transition states and how big the thermodynamic driving force between those two ones are too. But my point is, this is fully knowable. You can build a model that says, could this work or not? And more importantly, if you have something like a time course measurement and you're seeing blue shows up first and then over time blue is being reformatted to red, you can pretty quickly prove that that's what's going on, or you have a system that looks like this too. But rule of thumb, everything comes down to sort of like an order of magnitude or so can give you a certain amount of scale, but it's something that you guys are going to play with a bit. The most common, if you've ever learned about this whole kinetic versus thermodynamic control, usually in second year we tell you about the Wittig versus the Horner-Wadsworth-Emmons. This is the model that we usually approach this one as, is here's an example of a case that can be pulled under thermodynamic control versus under kinetic control. If you guys did 213 with me, you know about molecular patty cake for how you do your geometry optimizations. Do you guys know what I'm talking about? No? Okay, so we're going to do this really quickly. You guys, so this is familiar to you guys, right? This is the pathway for a Wittig reaction. In a Wittig reaction, you take a highly unstabilized carbanion, you take a carbonyl, so this is an sp2-sp2 coupling between the two faces, right? They are both sp2, so they are both achiral, right, to start off with. So that's why your left and right hands, this is your good mnemonic for sort of doing all your geometry controls. So they're planar, that's why you're using your two hands. When you do this addition, that addition is actually defined by a certain geometry stabilization. I'm going to bring together the two carbon centers. So let's say your right hand is going to be your carbonyl, where the palm of it is the carbonyl of your right hand, right? So this part here, this is the carbon from your carbonyl, where towards your fingers is the oxygen. So this is your carbon-oxygen pi bond over here. The large group is your thumb then, right? So imagine this is a R versus hydrogen out in that space. So there's my aldehyde or my ketone. Other hand, again, carbon on the heel of your hand. This case, phosphorus is up at your tip of your fingers. So what you now have is two dipoles. You have a carbon-oxygen dipole and a carbon-phosphorus dipole. Because of this dipole arrangement, you have, in terms of selectivity, bringing these two together, we're only going to bring together carbon with carbon, right? Your palms are, the two heels of your hands are coming together. That's the selectivity argument for the bonds we're forming. But you have two different geometries. I can come together fingers aligned or fingers opposite right now, right? That's our 3O and erythro points. As it turns out, just because of I have a carbon to phosphorus dipole and a carbon to oxygen dipole, lining them up anti like this, the trans dipole is way more stabilized. So it doesn't matter how I bring them together. I've already made the first geometry to my transition state where instead of coming together fingers aligned, you're always going to come together fingers opposite, right? That's just the consequence of the dipoles that you have. That's a specific event because of the orbitals that you're involving. Okay, now that I've got that, I still have these two flat planes, right? Given two flat planes, how many possible combinations can I bring them together where I have to go fingers opposite? 1, 2, flip both, 3, 4. Right? This is what we call molecular patty cake. 1, 2, 3, 4, right? What you're doing is you have two flat planes, and just based on 2 to the n, you have two combinations of each one. We have 4 possible combinations that you can go through. Now, if you look at the geometries that you're forming here, taking my two fingers and saying that they must be aligned this way, this one versus this one. So what I'm saying is AA versus BB, this is a topicity argument, right, between those two faces. Are these guys enantiomers or diastereomers to each other? That versus that. Say it louder. They're enantiomers, right? Because they're a perfect mirror image to each other. What we're saying is this versus this, those are two different enantiomeric outcomes of the same transition state. Versus this one versus this one, these are diastereomers to each other. So, and again, this, you guys know this, a flat molecule plus a flat molecule, if you bring them together in those four possible combinations, it will be two enantiomeric pairs of diastereomers is what you have to make. An enolate adding to a carbonyl produces two different diastereomers and two enantiomers of each diastereomer, right, if you have no other chiral control. And again, the nice thing is, just by that finger alignment one, we've got those four possible geometries. That's step one. So that's the first level of selectivity that you go through. You've put a specific argument in place based on those angles. Now what we have is an energetic argument saying I could make this one versus this one, right? Or this one versus this one. Now, based on those two, energy here and energy here must be the same, right? If they're enantiomers of each other, I have no ability to control that one versus this one. The transition state for these two must be identical. But transition state here versus here will be different. Now, based on just that, if we're only making this first intermediate, this is the first step of the Wittig, which of those two is going to be higher or lower in energy? So thumbs on the same side versus thumbs opposite. See, you know this because we did this in 230. Thumbs opposite, right? Because this geometry keeps the two bulky groups away from each other. Same thing as this one keeps the bulky groups away from each other. Versus this one's going to have a higher energy approach. The transition state towards this kind of diastereomer is going to be worse. So we can make the argument that given this approach, I'm going to expect that the anti-diastereomer, where these are opposite, will be lowest energy. Now you guys remember when we do the Wittig, right? To do the Wittig, to get over to here to make this double bond, we have to go through this betaine structure, right? This betaine structure is a result of first they're going to approach each other. You have this anti-arrangement, but then the oxygen and phosphorus must rotate together. So back to the patty cake, they hit each other. This is my stable one, but I now must rotate to get your fingers, your oxygen, your phosphorus to form. What happened to your thumbs? Same side. The geometry you generate from this Wittig means that the first approach will be kinetically favored, but then you go through a higher energy betaine to produce the higher energy product, right? The cis product across here. So again, that's a consequence of this transition state. And the reason why you get that is because this addition, that first carbon-carbon bond formation, effectively is irreversible. And it's only because in the Wittig reaction, the first ylid that you form, this guy right here, is so unstable that we go from a really, really high energy carbanion plus a carbonyl, and it is just so happy to not be a carbanion anymore because you've changed it from a carbon anion to an oxyanion. Think of the relative pKa's of those two, right? You've dropped down and you've actually stored your negative charge now as an oxyanion, so you are so much more stable once you made this. So they can sit there and break. The joke we make with the students is, this right here is that easier intermediate that you're like, yeah, I'm going to be I'll be a social scientist. I'm going to go into like banking. This feels a lot easier and stuff like this, right? But the problem is that does not allow you to move forward in the mechanism. And I can't break my carbon-carbon bond. So now I have to do the painful thing of going and changing majors or something like that, right? Now you go through something a later in life kind of problem. So you end up going through this high energy intermediate, but once this first decision is made kinetically, there's no way back. This is not a problem where you can ever re-equilibrate those two. That's where when we talk about the Horner-Wadsworth-Emmons, remember the HWE reaction changes this nucleophile into something more like carbonyl, phosphorus, OR minus, right? Your HWE nucleophile is now a ridiculously stabilized carbanion. The pKa of that carbon is in the neighborhood of an oxyanion now too. You've gone from something that had to be, carbon with a phosphorus next to it, pK of like 30 or something like that, you're deprotonating with Bewley, to something that's more like a malonate. The pK is sort of 18 to 20. So now you've got a carbanion that even if it made this first addition and it starts to try and do that rotation, well, you know what? There's a better way. I can back up, I can break, I can flip over. I can suffer this because I get through to a transition state after, which is now more stabilized. So they're going to be an anti-geometry of your product. So this is our classic example of the HWE versus the Wittig, is that kind of A versus B transition state that gives you your higher kinetically favored product, even though it's a higher energy product at the end of your alkene, compared to your thermodynamically more stable product requiring you to move through a kinetically unfavored starting material. Everybody remembers that part of it, and again, that story that we told you about that. There's a whole bunch of other reasons why that's not actually true, but it's a really good story. But again, that's kind of getting you in this mindset of back to, if you can see this, there are kinetic signatures that you can actually pull back out that allow you to say you have that kind of pathway. Another classic example is this one here. This is retro, Diels-Alder kind of addition, where you end up with the endo versus exo product. Once again, it just happens that because of approach control, formation of this kinetic product here, where you have this endo geometry, passes through a lower energy transition state. However, overall, thermodynamically, this geometry ends up being favored. I don't remember specifically why. Thermodynamically, that one gives you your lowest geometry across this one too. Does anybody else see it? The exo product here being, why would that thermodynamically be more favored?
I think from what I've heard before, and this totally could be wrong, but the exo, those carbonyls are a little bit more free and open, whereas
Here they're
endo,
restricted.
stuck under there is actually more congested than
Okay. That's an A-strain type argument, I guess. What you're saying then is, okay, I've got these hydrogens over here, and those ones are closer, but that doesn't make sense because you've got that over here. I'm not sure. I know this one too. This is the point we say exo ends up becoming thermodynamic, but I don't remember the core of this one as well. This is an example. Oh yeah, please.
Like if you don't have that bridgehead constituent there,
Then it doesn't work that way?
no, so like if that like the cyclohexyl ring at the top there was gone, like if it was just a regular norbornate, then this, I think it is just steric.
Okay. Yeah, I'm going to try and look up what that was again. What was useful about this, though, is that this is one of those simple examples. First of all, nice thing about this specific case, it is only one transition state in either direction. You do get two possible products, so you can actually run this reaction at different temperatures. You can measure it over time, and you can measure how much does this product form, but because this is fully reversible at the right temperature, you can actually form this product, and then as time evolves, you'll see it reformat to open chain and then reformat over here. So this is a case where you can actually put this in motion and watch the entire system pass out through equilibration. So the system I'm going to give you is you can build this in Copasi, and you can actually work it out where based on the individual concentration and distribution over time, you can fit it back to figure out what those energy levels will be. Now again, you're fitting the K values, but remember, those K values can be put forward using Arrhenius to say, based on these K values and that model, here is what my delta Gs would have to be, right? You can actually kind of move it through. So at a couple different temperatures, you can work out what the delta G double dagger left versus right happens to be, and then as a result of that, what the energy difference has to be. The overall product distribution over time is the ratio of those two, then coupled back against what you think the energy difference between these are based on different time point kinetics. So this is the basics of that kind of part, where once again, the hallmark of any of those things on a time course curve is something where you set up at a single product. In this case, the light blue curve shows up early and then is being depleted with constant mass balance over time where your other product comes back in. So this is the signature that you're looking for a system that's under this kind of control. So what this leads you into is, okay, those are simple examples. Typically what we're looking at with more complex surfaces is an actual full catalytic system where you have multiple transition states and multiple pieces. The thing that we want to sort of be able to do is, okay, given a diagram like this, the two really important parts of this come down to things like where your selectivity step actually comes in, especially with a multi-step catalytic system, and also where the selectivity based on the kinetics are too. So here's a case where, again, you're reading out this reaction starting here. You would be looking at a system like this where what we're trying to evaluate, this specific one happens to be a palladium-mediated oxidative addition, reductive elimination kind of pathway for either like a Suzuki or a CN type bond formation. So we're starting at this part here, and if we had two possible geometries, there's going to be a coordinate complex to make intermediate 1 versus intermediate, or intermediate prime versus intermediate, where if we were able to sort of measure those two, the concentration difference of those two at some point in the reaction, especially if this is where your steady state step is, will give you some example about which one of these two intermediates may be more stable relative to each other, but also the delta G of that particular system. The selectivity, though, going forward comes down to the two transition states. So what's happening here, and what we're usually seeing is a case like this, where we're starting at that middle step, there's a pre-equilibrium to a certain intermediate, but then after that, you're getting your actual selectivity forming step. So in this case, the second reaction here versus here is really what's defining what happens in this sort of case. So this becomes the first irreversible reaction on your overall sequence. So once you're over here, product A versus product B is just being determined by that energy difference. So this is where you have to have some visibility and understanding of what kind of a manifold that you're looking at that you can start to use. Now, in a selectivity network like this, and again, an example of something that we can use much more fluidly is something called dynamic kinetic resolution. So in a case like this is an example where what we have is an anti-product over here where we have two different stereocenters versus the syn product. Now, in a case of doing this with something like ruthenium binap, it's actually a reversible reaction where we can actually rapidly equilibrate between these two intermediates. So if we have rapid equilibration between that stereocenter over here, what we get is two possible geometries that is actually being fed back and forth. The reason what we're doing here, though, is we've got a very, very selective reduction that once that reduction is completed, we're actually using Le Chatelier to pull this equilibrium over. So you can also have the other case. In the first example, we have a very tight equilibrium right here that's sort of in the middle control, but once we're after that stereoselective event, there's no way back. Same thing here as we would apply that. We're in this part of the manifold. That's where we have rapid equilibration. We've got rapid isomerization happening over here. But then you're coupling that to a single stereoselective event or a single irreversible event that then holds the pathway constant. So something like a typical dynamic resolution that you may have seen before, the reason that we select for this product over here is not just because of a fast reaction, which is represented by that transition state. It's that fast reaction coupled to a rapid equilibration, which allows both of the two enantiomers of your starting material to actually be a single population. When you're actually going and modeling this, it means that even if I started with a racemic starting material, and even though I'm only reacting one of my two enantiomers away to one product, so in this case, I'm only reacting this enantiomer this way, effectively you consider both of these two in that concentration measurement because they're rapidly equilibrating to each other. You consider them as basically being a population of the same molecule, effectively, even though you have 50-50 concentration of the two enantiomers. Since I can rapidly isomerize between the two, we assume that that mass balance just says that they're all one population. So this is the basis for what we start talking about for rate control. So what we're going to do, we'll stop here for now, but the goal is to go back and review when we have a multidimensional surface like this, how do we look back at this and say where the transition state that's controlling the reaction actually exists? So in a simple system like this is back to our early, both Arrhenius type behaviors and other kind of components. When we actually get this through to multi-step transformations though, this is a case where it gets a little bit more difficult to look at this, and it goes back to one of the first articles I think we brought up of that whole idea of what's the meaning of the rate determining step. You know, the highest jump versus biggest barrier. So we'll kick off on that one again. Like either on Wednesday we'll continue on this point, or I'll get the midterm stuff up and running. Either way, by the end of the week we'll go through the full midterm review. All right, I'll see you guys on Wednesday.